So first of all, we're trying to create an ether, right?
Yeah.
So we're trying to create this ether right here.
Okay.
And we just got to show the arrow pushing for this. So the first thing that's going to happen is that this oxygen here is going to get protonated.
Okay.
So it's going to grab a proton from there.
Right.
This bond here will break.
Okay.
Right. Then once this has happened, there's going to be a hydrogen onto this oxygen here. So we would have this like that. Then this is going to leave. But it's going to leave as this guy comes in.
Okay.
So this guy is going to come in here, and this guy will leave. As this nucleophile comes in, this guy will leave, so it's going to do an SN2 reaction. Right?
Okay.
Then from here, let's see, just have a, so there will be positive charge here because this had a proton on it. Right. And now what's going to happen, we're going to get deprotonation of this guy here. And we would end up with this product here. And of course this guy will be protonated.
Okay.
And there wouldn't be a minus charge here.
All right.
Cool?
Okay. Cool.
Alright, so we're just making some additional changes on here. So this is not going to do the deprotonation. So the water is going to be the one doing the deprotonation here. Bond swings here, and this one will be like that. Then we end up with the product. Alright, so this is the next problem. So we have to draw the alcohol, right, and the alkyl bromide. So this is some kind of RBr, ROH, right? That could be combined. So we're going to combine both of these guys to generate the ether that is shown. And that ether that is shown is this guy here. So we got to figure out which ROH and which RBr will combine to give us this ether here. Right? So ROR is the genetic structure of an ether, where this here would be one of the R's, and this here would be the R, right? And we'll have the oxygen in the center.
Okay.
Cool.
All right.
So now we have to do some kind of substitution reaction. So we got to figure out if we're doing an SN1 or an SN2. So if we could either start off with this guy here or this guy here and react it with either this guy here or react it with this guy here. We got to figure out which one is going to be more favorable. So now this is our bromine, right? I mean alcohol halide. Now if we wanted, so if this was a combination we're using, this guy is not going to be a good leaving group, so we have to protonate him. And then actually no, that's not how the reaction will occur. Did he give us some kind of substrate to do this on? One second. So my guess in this problem is that this will get deprotonated. So we could either have both of these combinations, but it's more likely that this is going to happen.
Okay.
So what we're going to have occurring is we're going to have this bromine here, and this alcohol, and most likely there will be some kind of a base that will deprotonate this guy. Then he gets deprotonated, so we form this alkoxide. Then this alkoxide would then do an SN2 here, and that would then lead us to cause us to generate the product that we're looking for, which is the ether. Cool. So I think it should be this. So we're looking at this problem. This is the most common method for the synthesis of unsymmetrical ethers is the Williamson synthesis. A reaction SN2 of an alkoxide ion with an alkyl halide. Okay. Two pathways are possible, but often one is preferred. Construct the preferred pathway for the synthesis of 2-propoxypropane from propene. So this is where we're starting from. Right. This is where we're ending.